What problem does the proposed method aim to solve based on the paper's introduction?
The proposed method aims to solve the problem of feature selection for supervised learning tasks. The method leverages large language models, LLMs, to identify the most informative features for predicting a target outcome in a downstream training dataset. By prompting the LLMs with input features and the target outcome, the method aims to extract feature importance scores, rankings, or sequentially select features through a dialogue with the LLM. The goal is to demonstrate that LLMs can effectively perform feature selection without the need to look at the training data directly. This approach is particularly valuable in scenarios where the real-world semantics of input features and target outcomes are known, such as in healthcare, and can help in deciding what features to collect for predictive modeling. The method explores different prompting strategies and decoding techniques to optimize feature selection performance, showcasing the potential of LLMs in automating this critical aspect of machine learning tasks.
How does the proposed method for feature selection with LLMs work, and can you illustrate it step by step?
The proposed method for feature selection with LLMs works by leveraging pre-trained LLMs to identify the most informative features for predicting a target outcome. The process involves prompting the LLM with input concepts, features, and the target concept, then selecting features based on the generated output. There are three approaches to feature selection with LLMs. I. Selecting features based on LLM-generated feature importance scores. E. Selecting features based on an LLM-generated ranking. And E. Sequentially selecting features in a dialogue with the LLM. 1. Selection based on LLM-generated feature importance scores, LLM score. In this approach, the LLM is prompted to provide numerical feature importance scores between 0 and 1 for each input concept. High scores indicate a strong relationship with the target outcome. The top-ranked features based on these scores are selected for training the prediction model. 2. Selection based on an LLM-generated feature ranking, LLM rank. Here, the LLM is prompted to rank all input concepts based on their relevance to the target outcome. The top-ranked concepts are selected as the most informative features for prediction. 3. Sequential selection in a dialogue with an LLM, LLM-Seq. This approach involves iteratively adding features by prompting the LLM to select the next concept that would improve model performance the most. Features are selected one at a time based on their incremental contribution to the prediction task. Overall, the LLMs are prompted with specific templates tailored to each selection strategy, and the generated outputs are used to guide the feature selection process. The LLMs do not require access to the training data and can identify predictive features solely based on the provided input concepts and target outcome. The effectiveness of the feature selection methods is evaluated by measuring downstream test performance as the proportion of selected features varies, demonstrating the capability of LLMs for feature selection across different datasets and tasks.
What are the theoretical or practical benefits of using LLMs for feature selection compared to traditional data-driven methods?
The theoretical and practical benefits of using LLMs for feature selection compared to traditional data-driven methods lie in the ability of LLMs to leverage vast amounts of pre-training text data to identify informative features without directly accessing the training data. LLMs can generate feature importance scores or rankings based on the real-world semantics of input features and target outcomes, leading to strong feature selection performance. This capability is particularly useful in domains like healthcare and social sciences, where obtaining high-quality data is expensive. LLMs can effectively select features even without looking at the training data, rivaling the performance of data-driven methods like the LASSO. Additionally, LLMs can be used to decide what features to collect in the first place, showcasing their potential for guiding data collection efforts. The findings suggest that LLMs, especially at larger scales like GPT-4, exhibit strong feature selection performance, competitive with traditional methods, and are less sensitive to prompting strategies, making zero-shot prompting with no dataset-specific context a viable and efficient approach for feature selection. Furthermore, as model scale increases, LLM-generated feature importance scores show higher correlation with standard feature importance metrics, indicating the potential for LLMs to align with desired notions of feature importance. Overall, using LLMs for feature selection offers a promising alternative to traditional data-driven methods, showcasing their effectiveness, efficiency, and adaptability in various real-world prediction tasks.
How were the LLM-based feature selection methods validated or tested according to the paper?
The LLM-based feature selection methods were validated and tested by comparing them against several feature selection baselines using small-scale, low-dimensional datasets from various domains. The validation process involved using 7 binary classification datasets and 7 regression datasets, each with approximately 10 to 70 features after pre-processing. The performance of the LLM-based feature selection methods was evaluated by measuring how the test performance of a downstream prediction model changed as the proportion of features selected varied from 10% to 100% in approximately 10% increments. The evaluation metrics used were the area under the ROC curve, AUROC, for classification tasks, and mean absolute error, MAE, for regression tasks. The LLM-based feature selection methods were compared against baselines such as LASSO-Net, LASSO, forward and backward sequential selection, recursive feature elimination, RFE, minimum redundancy maximum relevance selection, MRMR, filtering by mutual information, and random feature selection. The results were averaged over 5 random seeds to ensure robustness and reliability of the findings. Additionally, the paper included detailed comparisons of the LLM-based feature selection methods against traditional data-driven methods on both small-scale and large-scale datasets, demonstrating the effectiveness and competitiveness of the LLM-based approaches.
What results were achieved with the LLM-based feature selection methods in the experiments described in the paper?
The results achieved with the LLM-based feature selection methods in the experiments described in the paper show that these methods achieved strong performance competitive with data-driven baselines, especially with sufficient LLM scale. The experiments demonstrated that LLM score, LLM rank, and LLM SEQ methods all achieved similarly strong performance, with GPT-4 consistently performing well across different datasets. The paper highlighted that even simple strategies like querying for an importance score one feature at a time can be effective for feature selection. Additionally, the experiments showed that zero-shot prompting with no dataset-specific context and greedy decoding led to strong performance, indicating that this could be a strong baseline strategy for LLM-based feature selection. Furthermore, as the model scale increased, the LLM-generated scores exhibited higher correlation with standard feature importance metrics, suggesting the effectiveness of LLM score in aligning with desired notions of importance. Overall, the experiments demonstrated that LLM-based feature selection methods can be effective, especially with larger models like GPT-4, showcasing their potential utility in various real-world prediction tasks.
What are the limitations or drawbacks of using LLMs for feature selection based on the findings in the paper?
The limitations or drawbacks of using LLMs for feature selection based on the findings in the paper include 1. Sensitivity to model scale. The effectiveness of LLM-based feature selection methods is shown to be variable across datasets as the model scale decreases. Smaller LLMs, such as Llama 2, exhibit less consistent performance compared to larger models like GPT-4, suggesting that a sufficiently large model may be required for reliable feature selection performance. 2. Prompting strategy sensitivity. The paper demonstrates that different prompting strategies can impact feature selection performance. While zero-shot prompting without dataset-specific context and greedy decoding is shown to be a strong baseline strategy, some prompting variations may not consistently improve feature selection performance across all LLMs, and in some cases may even degrade it. 3. Alignment with standard feature importance metrics. The study reveals that there is no specific notion of importance that LLM-generated feature importance scores consistently align with. While the feature importance scores exhibit higher correlation with standard metrics as model scale increases, there is still variability in alignment, indicating that further research may be needed to improve alignment with desired notions of importance. 4. Limited interpretability. LLMs generate feature importance scores or rankings based on their internal knowledge, which may lack transparency and interpretability compared to traditional data-driven feature selection methods. Understanding the reasoning behind the LLM's feature selection decisions may be challenging due to the black box nature of these models. 5. Dependency on prompt design. The effectiveness of LLM-based feature selection methods can be influenced by the design of the input prompts. While certain prompt variations may enhance performance, the optimal prompt design for feature selection tasks may not be straightforward and could require experimentation and fine-tuning. 6. Computational resources. Utilizing large LLMs like GPT-4 for feature selection may require significant computational resources and time, especially when processing high-dimensional datasets. This could limit the scalability and practicality of using LLMs for feature selection in resource-constrained environments. In conclusion, while LLMs show promise for feature selection tasks, there are limitations related to model scale, sensitivity to prompting strategies, alignment with standard metrics, interpretability, prompt design dependency, and computational requirements that should be considered when utilizing LLMs for feature selection.